When it comes to explaining relativity, you often see space-time diagrams, and they are great tools if you know how to use them. This will be a crash course on how to read a space-time diagram. So here it is, a diagram. Cool, right? Space on the horizontal axis, time on the vertical axis, right? We're already off to a bad start because it only measures time correctly on the axis. If we follow a journey at a different speed, the time doesn't match the axis. We have to use a Lorentz transformation. Never mind. Let's start again. This is here and now. This axis is our future, provided we don't change speed. It measures our proper time, the time we experience. Every straight line that starts at here and now is a different inertial reference frame, traveling at a different relative speed. To measure the proper time of one of these other inertial frames, we use a Lorentz transformation. This number here relates the relative speed of the inertial frame we're looking at to an arbitrary inertial frame, just to show you how I am transforming the diagram. A Lorentz transform is the mathematical tool that allows us to compare the universe at different relative speeds. The blue line is 0, but it's totally arbitrary. If we travel 5 seconds along our current path, we end up here. If we travel 5 seconds along another inertial path, we end up on a point along this line. Not the horizontal, but along this hyperbola. So why don't we just draw it like this? Well, it's only the 5-second line for inertial paths. If we zigzag, it takes less time to reach the line. Yeah, you heard that right. Also, the whole point of the diagram is to show light speed as constant. It makes it easy to tell what everyone will see. Watch. On a flat space-time diagram, all light is drawn at a 45-degree angle by convention. Anyone out in the universe who sees my here and now sees it along these lines. Everything that I am seeing here and now came along these lines. This is my light cone in one dimension. Are you with me so far? You may have heard about the relativity of simultaneity while learning about relativity. It's the thing that makes explaining relativity so confusing. Let me show you. Some people call this now or the present. It's everything happening now, but not here. We'll see it later. But if I Lorentz transform to another inertial frame, the line rotates, which means what I thought was happening now was actually happening later, or before and later. I didn't even go anywhere, and it's already confusing. But check this out. No matter what speed I go, the light I'm seeing here and now is the same, and so is the light I send out. Using our light cone, we can divide our space-time diagram into 3 different regions. All of this is things we've already seen, or the past.
Ow! Jeez, what was that for? It doesn't matter. It's in the past.
All of this is places we can go, provided we are fast enough. It is the future, but really many possible futures. But we can only travel along one path going forward.
It means your future hasn't been written yet. No one's has. Your future is whatever you make it. So make it a good one.
And what about now? In some sense, all of this is now, relative to here and now.
What the hell am I looking at? When does this happen in the movie?
Now. You're looking at now, sir. Everything that happens now is happening now.
How can all of this be now? Well, it is and it isn't. It's better to say these are things we haven't seen yet, we'll see it later, and places we can't go to or change. Why can't we go there? because it requires faster than light travel. We'll check that out in our next video. Side note to anyone else teaching relativity: please, for the love of all that is science, stop implying that events along these lines are simultaneous. What matters is when we will see those things happen. This does not depend on our inertial frame now, but on where we are later when the light from those events reaches us. The inertial frame is irrelevant. The edge of our light cone is included in this now area. These we are seeing now, and these connect us to now for someone else. Everything in between isn't connected to us yet, nor can we reach it, no matter how fast we go. Seems simple enough, right? 3 parts to the diagram, and because of the geometry of spacetime, they stay in their respective sections, no matter what inertial frame you are in. Watch. See? Everything stays in order. Let's review. This is here and now. This is the past, things we've already seen. These are places you can go. And these are places you can't go, but you will see later. This axis is the proper time of our current inertial path. These hyperbola are inertial spacetime distance lines. Well, I hope this helped you understand how to read a spacetime diagram. Next up, we'll look at faster than light travel on a spacetime diagram. And then also, why do we need relativity and why a Lorentz transformation? And then coming soon, space-time diagram lookalikes. Stay tuned and be sure to subscribe. See you next time.